Section. Introduction. As the size of AI models increases, the resources needed for generative AI applications also increase. This results in higher costs and power consumption for each generation from a prompt. Therefore, it's crucial to optimize text generation to reduce latency, infrastructure costs, and power consumption. This not only improves the user experience but also enhances the efficiency of text generation tasks. It's also important that these optimizations work well together. In other words, implementing one optimization shouldn't interfere with or prevent the use of other optimizations. There are several levels of optimizations that can significantly speed up the process without compromising overall efficiency. We provide an example of speculative sampling with KV caching in our code. Let's examine a set of optimizations that would be beneficial for many text generation applications. We'll consider the following optimizations for a full model. 1. Model-based optimizations. These are often problem-free when tested individually, like quantization, a common model-based optimization. However, unexpected effects may arise from the quantization and sampling of models. We won't delve into quantization in this article, but we'll focus on dynamic execution methods. 2. KV caching, or past value caching. This involves predicting the next value in a series of tokens and performing computations on these tokens to predict the next one. To avoid repetitive calculations on past tokens, the intermediate values are stored in a KV cache. This method is standard and doesn't affect accuracy. However, the KV cache can increase memory requirements. 3. Speculative sampling. This dynamic execution method uses a smaller, draft model to produce samples that are often good enough. Occasionally, candidates are rejected, and the full model is used when needed. This method has been published in several research publications with slight variations. To understand why speculative sampling works, let's revisit autoregressive sampling combined with KV caching. This process is memory-bound, allowing us to test multiple tokens on the target model simultaneously, at the same cost as sampling just one token. If we have a decent acceptance rate, many tokens are generated quickly enough to compensate for the extra overhead of generating on a draft model and then checking the batch of candidate tokens in a target model. Autoregressive sampling is a standard method of text generation in generative models, where next tokens are generated based on a probability conditioned on previous tokens. This could be followed by several methods to select the token at the next position, for example, argmax or randomly selected from top P. Note that sampling of models is memory intensive. We focus on a batch size of 1 for inference, but we can leverage a batch size of multiple words, sampled from a smaller draft model, to be evaluated in the target model together, taking about the same time as sampling a single token from the target model. For a reasonable value of batch size, we can leverage the smaller draft model for much of the text generation, using the target model less often for evaluation and single token generation when rejection occurs. This method has significantly increased throughput. However, the draft model and target model have different sizes that would be represented in a KV cache, so the challenge is to take advantage of separate optimization strategies simultaneously. For this article, we assume a quantized model and leverage KV caching together with speculative sampling. The authors prove that the target distribution is recovered when performing speculative sampling, guaranteeing the same sampling quality as autoregressive sampling on the target itself. Therefore, the situations where not leveraging speculative sampling is not worthwhile have to do with the case where there are not enough savings in the relative size of the draft model or the acceptance rate of the draft model is not high enough to benefit from the smaller size of the draft model. Section Summary. In this section, the authors discuss the need for inference optimizations in text generation models to reduce latency, infrastructure costs, and power consumption. They introduce 3 optimizations: model-based optimizations, KV caching, and speculative sampling. Model-based optimizations involve quantization and dynamic execution methods. KV caching stores intermediate values to avoid repetitive calculations but increases memory requirements. Speculative sampling uses a smaller draft model to generate samples, which are then evaluated in the target model. The authors demonstrate that leveraging speculative sampling with KV caching can significantly increase throughput without compromising sampling quality. Section. Selected optimizations. We're going to talk about how we can optimize the performance of machine learning models. This process, known as inference optimization, involves 2 main types of enhancements: model-based and execution-based optimizations. Model-based optimizations are changes made to the structure of the model itself, like pruning or quantization. On the other hand, execution-based optimizations are changes made to how the model runs, such as conditional execution, path selection, and caching. When we combine these two types of optimizations, we can significantly boost the performance of our machine learning models. In this discussion, we'll focus on the model-based optimizations provided by Hugging Face Optimum and OpenVINO, as well as two execution-based optimizations, KV caching and speculative sampling. Let's start with OpenVINO model optimization with Hugging Face Optimum. Optimum Intel allows us to load optimized models and create pipelines to run an inference with OpenVINO runtime using Hugging Face APIs. The Optimum inference models are compatible with Hugging Face Transformers models. This means we can simply replace the "auto" model for XXX class with the corresponding "OV" model for XXX class. In our case, we're using OV model for causal LM instead of auto model for causal LM. For instance, when we load a model using the from _pretrained method, we call it in a similar way. We can save the converted model for future use with the save _pretrained method. The tokenizer class and pipelines API are compatible with Optimum models. Next, let's talk about KV caching, also known as past value caching. This is a method where we store intermediate model values that were generated in previous computations. If we're using an autoregressive method for text generation, then we can use these stored calculations in subsequent iterations. This can significantly speed up autoregressive text generation, but the trade-off is that the cache can become quite large. Finally, we have speculative sampling. This method accelerates transformer decoding by using a smaller draft model for a short sequence of calls and uses the full-sized target model to qualify and accept or reject the projected results of the draft model. Other approaches, like build and assisted generation, use a similar method. The smaller models are quite good at generating much of the text, and validation, based on the full model, will occasionally reject tokens generated from the smaller model. This results in an overall speed up. However, there's a problem. A KV cache is standard for situations like this, and Hugging Face already enables such a cache by default. The main reason to disable the cache in a generative scheme is due to the memory requirements of such a cache. But speculative sampling requires two separate models, target and draft, which both have different model sizes and, therefore, different sizes for the intermediate values that are stored in the KV cache. As we sample from the draft model, the target model's KV cache can become stale, but we still do not want to have redundant calculations. So, do we have two separate caches? Is having a KV cache for the target model worth the memory footprint and the fact that its cache is only occasionally updated? To solve this, OpenVINO provides a collection of ready-to-run Jupyter notebooks to learn and experiment with the OpenVINO toolkit. We have provided a notebook with sample code to illustrate. The Speculative Sampling Notebook provides a clear example of how to take advantage of off-the-shelf models, like Hugging Face, exploit OpenVINO classes, and leverage multiple sizes of a model for speculative sampling, and compare it with autoregressive sampling. By default, the notebook uses GPT-2. If you have a machine with a lot of memory, at least 64 GB, you might want to try the DALL-E v2 models. Other models can also be tried. From our experience, it is best if the ratio of the sizes of the target model compared with the draft model is at least 10x. This should provide a good speedup in terms of reduced latency. Section Summary. Inference optimization combines model-based and execution-based optimizations to improve machine learning model performance. Model-based optimizations involve changes to the model architecture, while execution-based optimizations involve changes to the way the model is executed. By combining these optimizations, machine learning models can achieve significant performance improvements. In this case, the authors use model-based optimizations provided by Hugging Face Optimum and OpenVINO, as well as execution-based optimizations such as KV caching and speculative sampling. Section. Experiments. In our experiments, we put the DALL-E v2 model to the test by setting the value of k to 5. We conducted these tests under two different conditions. One where we limited the number of tokens generated to 40, and another where we increased this limit to 100. You can find the results of these experiments in the appendix.